Good morning. It's always hard to follow a funny speaker, so thanks, Josh. I also wanted to thank the organizers. We went to the event in New York a few weeks ago. It was a lot of fun, so it's really nice to be here speaking at the event. So thank you, Courtney and Nick. I'm going to talk a bit about what we do at Real-Time Data Solutions, Inc., focusing more on incorporating the real-time component into analytics and machine learning. I do want to tell you, though, that I am new at RTDS. I've been there for about a month and a half. So it would be great if you direct your difficult questions to my colleague Neil Couture, who's our CTO. He's right back there. So anything difficult, ask him. But I'll give you a bit of history of how this all started. Our co-founders are in New York City, and they were running a mobile advertising company. And they felt that there was a need that they couldn't meet with the existing technology that they had with the type of data and the massive amounts of data that they had. So they worked together with a group in Toronto, and Neil was there from the start, to implement a series of algorithms, and they put funding behind this technology to get this going. The challenges that we're facing were obviously the amount of data. You can imagine in mobile advertising, it's heavy data. The rate of data generation, number of attributes, and so on. And this is why the focus really for RTDS has been on the real-time data component. I like this figure here. I find it's a good analogy for analytics, machine learning, dealing with big data generally, is that it's the blind man and the elephant. And every blind man has access to one part of the elephant. So you can see there's multiple. The concept is that there's multiple truths to this. You can think of these blind men as statisticians, data scientists, researchers, whatever, companies doing data science. But there's the understanding there that there is, depending on what you're looking at or where you are, there are different answers. So we need to tackle this. What are the trends? I just got this slide from Information Week. It's comparing last year and this year, 2014 and 15, with respect to what is the interest in big data analytics. Where are the trends? What's increasing? You can see in most cases, the interest lies in correlations across multiple disparate data sources, so click streams and so on, so multiple sources coming together. Customer behavior, fraud or financial risk. There's security risks and all this stuff. And in most cases, the numbers have gone up in the past year. What's the market opportunity? I mean, I don't need to tell you guys, it's a big market. IDC reports, Gartner reports, they're all pointing to the fact that it's multiple billions of dollars. We're getting into the trillions of dollars. We're looking at, the Internet of Things, Internet of Everything market is increasing. Billions of devices are going to be out there. Everybody's obsessed with wearables these days. Bioinformatics market is massive and going to be growing. And really, a lot of this is streaming data. Real-time analytics is an important factor and still a bit of a challenge. So what are the verticals we're looking at? I mentioned that we were initially in the mobile advertising space. The technology was successful in that space, and so the co-founders, they really want to take the technology and bring it into other verticals. Verticals that we're very interested in, one is bioinformatics, computational biology. I'm happy about this because that's what my background is. I'm a computational biologist by training. So I'm really interested in how do we use machine learning, other analytics tools to look at genetics and proteomics, brain-related data, functional MRI, EEG, and other data types. How do we use these methodologies here? Financials, we're looking at behavior, patterns, and so on, Internet of Everything. Really interested in data that's coming at you in huge amounts and very fast. I want to give an example of brain disorders because I find brain disorders fascinating just because they're so complicated. If you imagine disorder X, there's obviously genes that are implicated. Researchers find out, gene X, A, B, and C are probably involved in this disorder somehow. Proteins are gene products, and you find a series of proteins that are implicated in a certain disorder. And then you look at the metabolites, there's symptomology and behavior that's implicated, let's say, in Parkinson's or Alzheimer's or whatever you're thinking. And then we can look at disorder Y. And in brain disorders in particular, and many other disorders, there are genes that are shared across disorders. So gene A, B, or C could also be implicated in disorder. It could be implicated in disorder X and disorder Y. Proteins could be shared across disorders. Symptomology and behavior. Depression is a good example. Depression runs across multiple brain disorders. Parkinson's, Alzheimer's, epilepsy, cerebral palsy, traumatic brain injury. So how do we find those patterns? How do we find where those more comorbidities exist and use the methods that we have to answer these kinds of questions? Some of these questions are listed here. How do the genes and proteins relate to each other in specific disorders? Can we use clustering or regression? What other factors are involved in disease onset? What about environmental factors? What about nutrition? Now we have tons of data coming in. So patients now can use a lot of wearables. They use their smartphones for entering information. Patients are a huge source of data these days. What else can we use? Natural language processing, other methods. And how do we combine all of this data together and make sense of it? So how do we combine the genetics with the proteomics, with the EEG data, with the environmental data, with the nutrition data, and use machine learning and analytics tools to find better answers, to find more answers, and ask questions that we didn't even know we had potentially. I like IBM's slide. This is IBM's slide. It talks about the 4 V's of big data: volume, variety, velocity, and veracity. And I think it's helpful in breaking in technology companies like us in identifying exactly where is it that we can have an edge, where is it that we can help solve problems. So if we sort of take that perspective and look at what have we built at RTDS. Right now, we've built a system called SymetryML, and it's a distributed GPU-implemented predictive analysis modeling technology. And it's good where you've got massive data. We've finished version 3.5, and it really focuses on exploration, so basic stats on your data. And then we also do a lot of modeling. We do classification, regression models, and Markov chains. I'll get into that a bit later. We're working on version 4.0, additional features, but really where the orange square is where our focus is and where we have things developed. Before that, on the data management, data capture, storage, there's a lot of companies here that do that. Data pre-processing, but we're interested in those things as well. For example, on the data pre-processing side, what are those technologies that we can layer with to make this a more effective technology, for example? How is this technology addressing some of the challenges that the co-founders were trying to look at initially? It's about heavy volumes of data and streaming data. So this is where the real-time component comes in, is they need to get quick answers with the data that we're looking at with the mobile advertising data. I've talked about the GPUs. We're also interested in FPGAs, writing this, deploying what we've done, porting it to FPGAs. We have a web UI that it's easy to use, it's very simple, but if there is interest in sort of testing out the technology, we also have RESTful APIs that could be integrated into existing systems. And so the modeling and the exploration of the data is done in real time. And I mean, I was interested in this because I knew there was so much data of this kind in hospitals and with patients. And how do we use these technologies to give back answers quickly to clinicians, for example? How do we analyze this and tell the clinician right away that, you know what, looks like there's a pattern here. This may not actually be disorder X. You may want to think about the, Y and Z as well. So this is about getting answers back quickly. This is a little bit about how the flow of the technology works. The data comes in. We have a learner, and then the statistical representation of the data. The way we represent the data in our system is what makes it fast. So this is the proprietary bit, I guess, and then the exploration is done on the data set, modeling, and predicting. This allows you to build thousands of models at the same time. So you can tweak your models, build models. The file size is not important. You can have an infinite number of rows, and it will generate the thousands of models that you need for you. Scales linearly. And also, I think one of the things that I like about the system is that it's actually very simple to use, and it's simply deployed into your favorite language. A few of the key features, again, this is about how the actual core technology works, is that it deploys incremental, decremental learning. So when you add in new data, you don't need to rescan the file. And I think this is what makes it a real-time technology. So you just update your statistics and you update your models based on updating the internal representation that's there. We've developed parallel processing, distributed computing as well. You can add variables on the fly, and there's a lot of functionality for you to do variable selection and tweak your parameters or change whatever you want about the model. Some of the component technologies are listed here. We have a web user interface, we have RESTful APIs, and they're written JavaScript and Java, C++, and right now we're using NVIDIA GPUs for our work. A little bit of the core functionality for SymetryML. Some of the analytics that we're doing, there's a univariate analysis. This is just the basic stuff, mean, standard deviation. And then we've got some of the bivariate analysis, so you can look at correlations of your data, correlations of a variable with respect to other variables. Hypothesis testing, chi-square testing, ANOVA, and so on. And then you can build models, do predictions, assessments, and persistence as well. I just want to show you the user interface quickly. It's very simple. This just shows you some of the univariate analysis that you can do, variance and mean, standard deviation, so on. This data set is actually a mobile advertising data set that I used for this example. This is the continues on with the exploration screen. This shows you the correlation screen, so each variable correlated with all the other variables that you're interested in. And then modeling, it tells you how long it took to build your model. Usually we do it under a second. Models are built very quickly. You can build hundreds of models at the same time, and then assess your models. And this is an assessment of an LDA model and tells you how well you did. Models we built, we can build regression models, so multiple linear regression. We've got another one, and we've got classification models. So we've got LDA, we've got QDA, we've got Bayes models, and we've got Markov chains as well. But we are interested in what other algorithms can we layer on to that are well suited for our technology. We can't do everything. We can't. Some of the algorithms out there aren't well suited for our internal representation, but there are some that are, and we want to learn. We're doing research into what those are, but we would love to hear your ideas on that as well. Where are we right now? We have a team of 6 engineers and data scientists in Toronto. We have our board and our co-founders are in New York City, and our focus really is on the technology differentiation. We've met multiple milestones in the past year and a half. We have proven this technology in mobile advertising, but we're interested in other spaces. So we've also tried this technology with microarrays, so genetic data, and it's done well. We're doing more research in the area, but we want to extend this. We want to look at, more genetics research, proteomics research. Where else can we take this? I think a promising area is EEG data, just because it's so big and it comes at you very fast. You can get terabytes on a single patient in 10 minutes, for example. We're looking for beta testers with really great data sets for example, in the health space, in the bioinformatics space, computational biology space, also in the finance space. So we have actually one of our colleagues is really focused in on doing research on the finance side. Internet of Everything is another area of interest for obvious reasons. So if this is you, come and talk to us. We're very interested in testing out in beta users. We're also looking for integration partners. So if your technology would layer onto ours nicely, we're really, we'd really like to hear about that as well. And we are working on our next version, so 4.0. It's going to be fully parallel. We're using Apache Spark. And we are adding on, we're hoping to add on additional algorithms. And so that version will probably be available the next few months, but that Neil will tell you more about that. So thank you very much. These are our emails, and we'd be very happy to hear from you.